Hi everybody, in this video I would like to talk about two corollaries of the monotone convergence theorem. The first one is a probabilistic version of Tonelli's theorem. And that says the following: if xn's are non-negative random variables, then if I take the sum of the xn's and an expectation of that, the infinite sum, that is going to be the same as the infinite sum of the expectations. Okay, that's the statement of the theorem. Let's prove this. The proof is very simple actually once we have monotone convergence in hand. The proof is the following. So let yk equal to the sum of n from 1 through k of the xn. Okay. Now the xn's are non-negative, so we know two things about the yk's. First of all, the yk is non-negative, and we also know that these guys, as a function of k, are non-decreasing. Again, because the xn's are non-negative. So if they are non-decreasing, then we know that monotone convergence applies. So if I take an expectation of yk, well, let's do the limit as k goes to infinity of yk, this is going to be the same as the limit as k goes to infinity of the expectation of yk, and that's because of monotone convergence. I can use monotone convergence because the y is non-negative and it's a sequence of non-decreasing random variables. But if I extend the left-hand side, what is on the left-hand side is the expectation of the limit as k goes to infinity of the finite sum up to k. What is the limit of the finite sum up to k? Of course, is the infinite limit of the xn's. What do I have on the right-hand side? Expectation of yk is the expectation of the sum of the yns, and it's a finite expectation, and therefore it swaps with the expectation. The sum, it's a finite sum which swaps with the expectation. So the expectation of this finite sum is the finite sum of the expectation of the yns. What happens when I take the infinite limit? When I take the infinite limit, then this finite sum converges to the infinite sum, and I have my statement. Expectation of yn. That's the end of the expectation of xn, apologies. This should be x, this should be x, and this should be x. So now it's the end of the proof. Okay? So that was Tonelli's theorem. Let's see the next corollary. The second corollary is Fatou's lemma. Which says the following. So let x1, x2, and so on and so on, and also y be random variables. Let's assume that the xi, so all of the xn's, let's say xn's, are bounded from below by y, and as before in monotone convergence, e of y exists, and it's not minus infinity. Okay, so then notice that I don't have any assumptions on convergence of the xi's. These are any random variables, they are just bounded from below by this other random variable y. If I look at the set of the expectations, the sequence of the expectations, I have absolutely no assumption on this. This could be anything. But in any case, I can always take a lim inf of these expectations. And I could as well take the lim inf of the random variables themselves. Again, I don't have any assumption on the random variables, but lim inf always exists. And I can take an expectation on that one. And Fatou's lemma tells me that one is larger than the other, namely the lim inf of the expectations is larger or equal than the expectation of the lim infs. So that's Fatou's lemma. Okay. How do I prove this? How do I prove this? The proof goes like this. Define Zn as the infimum of the xm's when m is at least n. The infimum of the xm's when n is at least n. Okay, what do we know about this? Well, there are two things we know. First of all, we know that all of the xn's are at least y. So for every omega, this is at least y. That's the first thing we know. The other thing we know is that this thing is non-decreasing. This is the second thing we know. Why is that? Because if I increase n, then I'm taking the infimum over a smaller set. Taking the infimum over a smaller set can always only increase my value. It can never decrease my value. So I have actually a non-decreasing sequence Zn, which is bounded from below by y, which has a finite expectation at least from below. And that's the ideal circumstance to make an application of the monotone convergence theorem. So let me start on the left-hand side with the expectation of the lim inf of the xn's. Now, what is the lim inf of the xn's? The lim inf is actually exactly the non-decreasing limit of the zn's, the non-decreasing limit of the infimums after index n. That's how the lim inf is defined. So actually this left-hand side is equal to the expectation of the convergent, the limit of the convergent zn's, and this limit exists because Zn is non-decreasing, and it's exactly what the lim inf of the xn is. Now here comes monotone convergence. Zn is larger than or equal to y and non-decreasing. So here comes monotone convergence. And that tells me that this limit actually swaps with the expectation. So I have the limit as n goes to infinity of the expectation of the zn's. And this limit, of course, exists, well, for two reasons. First of all, it swaps, but also the expectation of the Zn is monotone non-decreasing, at least, so the limit exists. And then, if we have a limit, then a limit is always the same as the lim inf. For any convergence sequence, the limit and the lim inf are the same. So then I have the lim inf of the Zn, or E of Zn. However, the Zn, being the infimum of the xm index starting from n, I know that for every n, the Zn, just by the definition of it, cannot exceed xn, just because it's an infimum taken of a set that contains xn. So Zn for every n cannot exceed xn. And therefore, on my right-hand side, I know that the lim inf of the E of Zn cannot exceed the lim inf of the E of xn. So the E of Zn itself cannot exceed the E of xn. And therefore, my right-hand side must be smaller than or equal to the lim inf of the E of xn. And that's the end of this proof.